I'm Jim Gray with Moose Mountain. I've been to these seminars since one, I think. But I've given presentations on the KSM project before. This isn't about the KSM project. I just wanted to, what we wanted to do was use it as a case for block caving. A lot of the things we do at Moose Mountain, a lot of open pit mining and hard rock, and everybody keeps saying, well, there's an underground underneath, and they all say, well, we can block cave it because it's $5 a ton operating cost. So we just thought we would use this to explain some of the issues at KSM of why they are going to go block caving under the pit, and then hand it over to Fred to sort of say how to optimize that, because you just don't block cave. So I'll sort of concentrate on defining the situation and then hand it over to Fred so he can optimize it. Okay? So pre-feasibility study for KSM was published. Everything I'm going to tell you is public document, so I'm not telling any secrets. You can go on CIDAR and see the open pit study that was done in June 2011. We are currently updating the pre-feasibility study, and it'll be coming out in a month. And it does include an underground, and Seabridge, the owner of the project, has said they will have a combined open pit and underground plan. So just where are we? That's Canada, the country to the north that gives you all the snow. And we're in British Columbia, and the KSM project is inside the Alaska Panhandle. There's a highlight of other projects in the area. In British Columbia, everybody lives down here. Halfway up the province is virtually unpopulated. We're doing a lot of big copper gold projects up in here. And the past producers of Grand Duke, SNP, and SK, the KSM projects right there. There's 3 ore bodies. The Iron Cap, Mitchell, Sulfrets, and Kerr. They're all quite separate. The one thing I want to point out in this slide is the valleys with water. The rivers head out of Canada into Alaska, so we've got 2 regulatory regimes to be concerned with. This is all ice. These are ice caps. They're not glaciers. These are glaciers. So the ice flows off the ice caps down through the valleys. And the Mitchell pit does show it impacts the glacier, but by the time development gets there, we've timed the pit pushbacks to stay out of the glacier because it's receding about, over 30 to 40 meters a year. Property was found in the 60s, the Sulfrets and Kerr, which were on mountaintops. You'll see in some of the other photos that the Mitchell deposit in the 60s was covered in ice. So it's retreated back and exposed. This is the the major target. Typical high terrain, steep valleys, high mountain tops, ice caps, glaciers. But in reality, that was an exaggeration. It's still very steep, very high. You believe me too. That's 8 kilometers across. So that's the Kerr deposit, that stain up there. The Sulfrets is right here. And there's the Mitchell, that stain right there. So the glacier in the 60s was down here. And Iron Cap is just off the photo up there. So an open pit, where do you put the waste? Stay out of a river. So we're going to concentrate on the Mitchell and Iron Cap, but mainly the Mitchell. So there's a highlight of that. You can see there's the ore body. The mineralization at one time was up here. The glaciers, carved it out. Very hard rock. This has resisted glaciation. It stands very steep on a natural slope to make a great high wall. The open pit plan I'm going to show you has it mines 400 meters below this point, and through the mountain peak is a 1,600 meter high highwall, and it geotechnically passes. But you can see that strip ratios on the first phases is almost, very small. In fact, you could mine here with no waste stripping. But as you start, the top of the mineralization's right there. So as you start running these things up, the strip ratio takes off on you. So it limits out quite quickly. It gets the cost of ore release at the bottom takes off. Life of mine on that all open pit was just one thing to point out is the mill is over here in another valley, and there's a 27-kilometer tunnel. So the ore is crushed and conveyed under here in the twin tunnels to the other side. There's no place to put tailings pond over here, so we had to go to another valley. That's the Mitchell pit, 1,600 meter high wall. The iron cap is up there. So the waste has to go up these valleys. That's the Kerr pit, Sulphret's pit. The Kerr ore will cross on a rope con, so it's a rope suspended conveyor where the conveyor is, you put two support ropes, not a bridge, but just support ropes across the valley. Whoops. And there's no idlers. There's rollers on the bottom, bolted to the bottom of the belt, and they go running across these. So, and then there'll be a tunnel through this ridge to get that ore over. Waste has to go from here up to this dump because there's a water treatment plant. We don't want any waste dumps in here because of acid rock. So everything goes up there, and that is water treatment forever. This river here gets diverted through here with twin tunnels. There will be a hydro dam and hydro generation forever so there's electric power available to run the water treatment plant forever. And in regulatory terms, forever is 200 years. So there's some dimensions on that. You can see open pit issues as you do your pushbacks from here and you advance farther up. Every time you got to climb this hill. And not only is the strip ratio getting greater, but the access cost is getting significant every time you climb up. And the trouble with iron cap was there was more than that. Over 100 meters of ice to take off there. We were going to dump it in here and create a ice dump. And then, here's just a side view of the waste dumps. So that's the water treatment plant. So you got to get this waste up these high dumps. So it's significant in that terrain. It's also one of the highest snowfall areas in the world. So open pit mining has a lot of things to deal with in snow. Just a summary of the all open pit plan. It's a big project, 2 billion tons of ore. The strip ratio is just under 2.5 to 1. And under this reserves, there's almost 40 million ounces of gold and significant copper. So it's a big project. So if you're going to go underground, there's some things to consider. A thin vein underground deposit is going to produce at about $120 a ton or more. Very thin veins, lots of labor-intensive, small equipment. You can go to some big stoping methods that are, down in the $20 per ton. And these are operating costs, doesn't include the development to get there. And with these big porphyries, they're relatively low grade, and so you need to go some kind of bulk mining for a low cost. And there's a lot of people out there that say you can block cave for $5 to $10 a ton. Now that's after development. So everything's got to be in. The other trouble with block cave is you got to get under the whole ore body. You can't slice your way down. You got to go all the way underneath, put in all the development, and everything's in before you can start producing ore. You don't start producing ore on your way down. So let's talk a little bit about block caving, the elements of block caving. You're going to have to get underneath the ore body and build all this stuff under there. So the principle is to undercut it. And then it lets the stress that builds up, you got to get to a minimum width where the thing starts to collapse on its own because you're not blasting the ore. And the stress builds up. You then have to draw it out. So you have all these drawbells. And they go down to the production level. So the scoops come in here and start mucking out under the drawbells. They pull it down here into the ore passes. The ore passes go down into a crusher, goes down into the transportation level, and then up and out of the mine. A lot of development. It collapses at its own rate. And the block size has to be predicted because it has to fit through the chutes. You can precondition it. They will do some blasting or hydrofracking up here, but that increases the cost. And if you get large pieces, you start blasting in your draw points, but you're trying to get all the whole 200 meters of stope has to come through that draw point. So you got to take care of your draw points. The other thing is you draw out to keep a small air gap so it relaxes and cracks. You don't want a big air gap because if a big slab comes down, you get a tremendous air blast. So underneath that extraction level, so the extraction level, above these were the bells, and then the extraction level down to the crusher or a breaker, that's service level, and then down into, this is an ore pass, and then you probably have a big train haulage system. This is a 20-year mine. So you put in a train, takes it over to a conveyor that takes it up and out of the mine. So that's got to be in before you start. So there's the decline for access, and that'll be the conveyor way. Inlet air, exhaust air. There's on this mine plan, there's 1,200 draw points. So there's a significant amount of air coming out of this thing. The open pit mine is mining at 120,000 ton a day. The maximum I think we can get out of an underground is 40 to 60,000 ton a day, which is enormous for an underground. So those are all the development that has to be in before you can start pulling this thing. We're predicting that the development time on this is about 6 years and, significant cost. So why would you do that? Well, here's the open pit. There's the ore body in the valley bottom. This is just Mitchell Pit. That's the valley. This is not vertically exaggerated. So as you can see, as the LG shells go down, the incremental strip ratio on here gets up very high. So if you put in an underground underneath here, and you put all that development in as a sunk cost, then taking more, this was the economic pit limit, but if this was mining at $5 or $10 a ton underground, adding to the stope, well, at $1.50 mining cost, at a 10 to 1 strip ratio, that means you got 11 times $1.50 is the cost of the ore right there. It'd be cheaper to take that ore with underground. Just add it to the underground and take less pit and generate a lot less waste for those big waste dumps. And the waste dumps cause the water treatment issues. So those are the incentives to go underground. There's just a little curve. Now, yesterday they told us they've got software now that'll automatically do that curve for you. But, so, if these are the pit shells from the LG, and that's the incremental strip ratio and the accumulative tons, right? So, as the phases go up, if your underground cost was $5, the competition says the underground's cheaper than the open pit there. If it's $10, we're up to where our ultimate pit limit was. So if we can get a a block cave somewhere between there and there. We'll cut off the open pit and go under, add that tons to the underground. And plus add the extra tons below the ultimate pit. Considerations and incentive for underground. So you do the comparative cost of the open pit. It doesn't have the adverse topography. Well, if you have adverse topography for open pit, then maybe that justifies the difficulty of underground access. Less surface disturbance. Extreme snowfall in this area, so you don't have to fight snow, but you do have to fight the runoff water. There's the issues of river diversions, limited waste dump rooms, and with less waste, you got less water treatment in the waste from the waste dump. So, it's up to you, Fred. Now you're going to optimize it.
We're not going to optimize.
Boy. I think I need my sunglasses up here. Anyway, the block caving stuff. Actually, we've been doing little bits and pieces of block caving in the system for probably 20 years. But as you can see from some of the talks you've given or been given here, we do a lot of tricks and ways around the system to put data in and do things outside, bring it back in. So about 10 years ago, we brought some of those tools into an easier workflow. And I'm going to show how we applied it to this project. So I'm going to go through a few basic concepts, the steps we go through, and an example for KSM on how the block caving works. This is a level of detail, is more conceptual, more like an economic planner than it is like SP or SO at this point. Okay, so the short story is that we have to approximate what kind of dilution we're going to get by mixing the material. Most block caving operations, usually from the bottom, the columns, you'll have higher grade material, and up above it'll be lower grade. So what's going to happen when you draw the material down, there'll be mixing, and the dilution or the lower grade material on the top is going to come down and mix with the material below, and actually some of the higher grade material below is going to move up. Because it mixes. So we have a methodology of approximating the dilution caused by mixing. The one method we're using is something devised by a guy named Dr. Lobsher years ago, and it figures a way of diluting the columns vertically. In this particular case, it isn't very meaningful because this is such a homogeneous deposit. Anyway, then we compute the footprint, as they call it, which is we choose a production level above which we're going to have our column or drop, and we determine the column heights and the economics. And if we lay that out and look at it and figure out the column height or the economic columns and plan, it becomes the footprint of the block cave. Now, the block caving, you don't have to have it all in one. You could have multiple levels, but we're just talking about one level here, or one production level. Then once we have this footprint, we outline where we limit it, because on the edges it's probably close to uneconomic, so we want to just mine the more favorable material. And we may subdivide it into smaller areas because we'd like to mine the higher grade columns first. But there's a lot of geotechnical considerations and practical considerations on how you would do this, so it's not just, it's like Jim talked about the stoping the other day. We were talking about, well, you could go and mine each of the stopes, highest grade, the lowest grade, but you'd have a little trouble getting access to them, so it's not that simple. Anyway, so then we outline the areas where we're going to have draw points, and then we can develop a sequence of mining. Basically, within each area, we give it a direction, and it builds a sequence code. We simulate mining at each draw point to create a schedule, and then we end up with reports, visualization, and graphs. So, It's all very simple. The data files and the way we do this is all built into MineSight files. We'll have a block model that we'll add a separate set of diluted grades to, and all the calculations will be read, everything will be read from the block model and written back to either the block model or a GSF file. The mining geometry and the sequence of opening the draw points is stored in this GSF file. Basically, as you all know, a GSF file is just a whole bunch of surfaces. Well, what we store in there, in addition to when we analyze the draw, I'll get to that. More details later. And the mining production, the mining progress is tracked by saving a timing code in each block as to when it's mined or when it's drawn down. It's actually done by period and day within period. And then but the block model remains an in situ model. We don't really change the geometry of it during the process. So, actually, draw points. The draw point, when we start with the block model, we've got these rectangular or columns going up, and it's based usually on whoever built the model figured out the block size based on either drilling pattern or complexity of the geology, so on. And it may be completely unrelated to the size of these draw points. So there are two ways of us handling the model. One way is we actually just use the columns as draw points, which is the simplest way at this point, since we don't have very much. Or we can overlay a pattern of the draw point geometry, and then we composite the data into columns above each draw point. And it looks something like this when we composite them into columns. It's basically another form of the block model, but each column is not necessarily a rectangular shaped block. It's based on the geometry of the draw point. Anyway, so next, to develop this footprint, we basically put in mining and development cost. Development cost is, as Jim pointed out, there's a heck of a lot of development cost just to get down to the elevation where you're going to have your draw points. But every draw point requires a lot of development cost and time as well. And you can't just go down there and open up and get to maximum production in a very short period of time, because you continually develop these draw points. But anyway, there's a development cost for each draw point, and there's also a maintenance cost for the columns. As you go up in the columns and draw from them, you'll have to refurbish the draw points and do extra work. We put metal prices and recoveries in. We can use different areas, and in this case, we actually have two areas we're looking at: the the Mitchell deposit and the iron cap. And then we'll choose a production, elevation to try. Now, we don't obviously know when we're starting out what elevation is the best one for having our production level. So this is what we would do is develop the footprint on all the possible combinations and then determine which one is the best. So this is what the footprint would look like displayed out of a GSF file. What we have here color-coded is in each block, we have the value of the whole column in thousands, and we have the average value, and we have the height and the diluted grades. And so what we can do here is we can digitize or draw an outline of where we want to actually have the mining proceed. I mean, we don't want to mine this blue color is not very valuable columns. They're probably close to break even. And so we want to outline some kind of area like this. One thing that's interesting about storing this inside the GSM the way it is, you can actually take IP and apply it and interactively, instantly calculate the areas in tons and grade in each of these areas very easily. Because you have the column heights. So once you decide and pick out, smooth these areas out, then within them you can put a code and tell which direction you're going to mine. As you can see here, this is going to be mined this way, and this one's going to be mined this way. The color code is just based on the mining direction. I know this is very colorful and odd drawing, but what it's showing is, it's showing the complete columns that are being mined, and the colors are showing the timing for the mining. So over here, these are the columns that are this is where mining starts, and the heavier blue is drawn the first year, and the lighter blue, and then so on. So what that's actually shows what's being drawn in each year. So you can see that material being drawn in a particular year would be look something like this in situ, but the actual geometry is going to change, so that, say, when we're up at the point this material here is being mined, and we've already depleted all of this column all the way down, so everything here would just drop right down. We're going to, I think Jim had some drawings of this, but we can model what would happen. You drop the material down, then you have a swell factor, and then you'll have to smooth off the subsidence. But it's not as simple as, well, what happens is a lot of geotechnical complications, let's put it that way. Anyway, so this is KSM. So this is where you can see here's the pit area, and this is the ore body below the pit, and then up here in this wall is the iron cap deposit. So the steps are, in a little more detail, we have a procedure that will automatically build you a new block model with extra items in it in the GSF file. Then we do our column calculations, as I explained, to get a footprint. We define the areas. We redefine, once we define the area, we recalculate for that production level we've chosen. And sometimes, with the deposits not so homogeneous, you may have columns that adjacent to each other that have a big gap between them in elevation. So there's a function in here that'll smooth off the tops of the columns. And then we sequence the columns, and then we do our scheduling. So this is another picture of the footprint, but this is for KSM. And you can see here on the side, at least you can see, I don't know if I can see it. Again, we've got the items that are stored away in the GSF file. These are the copper grade, the diluted copper grade, gold grade, moly grade, and silver grade. This is the height of the column. Actually, when I tested it out or tried it here, I allowed the column to go as high as it wanted to. So this is a very unique block caving operation. We've got 450 meters of draw at that point. And down here you can see there's the average value for the column in thousands, so that column's worth $10 million. And as I say, it's just using the columns are the blocks, not actual draw points. There's another view of what you can see. There's the footprint down here, and this is the columns, and this actually is the pit bottom. I didn't have Jim's bottom, the pit, so I just took the elevation that they had another study done on this, and I just designed to let the pit design program, I went and designed a bottom at the elevation that seemed reasonable, so it's not quite it's a little bit larger bottom than we might have. This is another view of what it looks like. This is down here. This is the footprint for the Mitchell, and this is the elevation at the top of the economic columns, and then the color is actually the value of the columns color coded. And this is the same thing up here for the iron cap. And these little remnants out here, of course, wouldn't even be mined. This is just showing what it would look like. overall. The scheduling is based on, well, the most important factors in the scheduling is, of course, the draw rate on each of the columns. And we're assuming what happens is that the draw rate varies as a function of the material and basically as the height of the column goes up. In this case, we assume that the draw rate for each column gradually increased, and we didn't have any information about the material characteristics, but there's a lot of geotechnical information to be gathered with this. Then we also, the next variable is our draw point development rate. Like I said before, you can't develop and start mining at full production instantly, so we tell it the area we can draw. Since we're using these columns instead of actual draw points, what we use to specify the development is square meters per year, and instead of and our development costs are per square meter instead of actual draw points. And then we feed in the plant capacity. So it's not an automatic scheduling process in that you can, as you vary and simulate the scheduling, you'll get a result, and that result may it may take you 330 days to reach your plant capacity or 350. There's no direct calculation. You have to sort of like trial and error sort of calculation. So the scheduling creates a yearly and daily schedule actually in a separate file. So if we wanted to see what it looked like any particular day, we could see what blocks are mined. Of course, that's a little bit overkill. And it stores back in the block model this information. So this is just showing again the footprints for the two areas, and it's showing the color coding the material as to the period that it's actually drawn. Another picture. I just like the colors. I don't know if it's any more descriptive, but so how would you? Jim talked about optimization. Well, I hate that word because, well, like remember what Mike said earlier about the mining dilution, saying that the limits on how well we can define the dilution. Well, with block caving, there's a lot of things that are going to cause problems. The draw rates, the way the material breaks, and the amount of dilution. I mean, obviously, as I explained, we estimate the dilution in the beginning by this vertical dilution method, but when the actual material starts getting drawn down, everything will change. And we have no way of really modeling that, even though there are some sophisticated tools to do that. At this point, we don't have enough information to use it. So anyway, the way we would try to maximize NPV, and I say that instead of optimize, is, okay, we pick column heights. When we do the column height calculation, I guess I assumed it was obvious what we do is we go up the column and accumulate the material and pick the height that has the maximum total profit. And if we want, we can build a profit into that so we don't mine. We can limit it to, so it isn't going to mine some low grade at the top. We limit our footprint to mineable areas. Then the way we sequence within the footprints and the boundaries, we obviously try to sequence to maximize the mining of the good stuff early. The kind of reports, the data, what happens is the program sends some data out to some files, same types of files MSEPC uses to graph, but later on, it's kind of the same as ARC technology. And this shows during the course of the mining the capital investment required. It's divided up into two parts, developing the draw points and maintenance. This just shows, and this is the important thing, this shows as you mine, this is your production, and you can see that well, it's actually the area available at the end of the year to draw, and that's when you reach your maximum production. So it takes actually in here 5 years before you're at your maximum production rate. This is just showing the average draw rate for, because the draw rate varies, as I said, as you increase the column height. It perhaps doesn't increase this much, but anyway. This is another graph showing the production, the cumulative net present value, and this gives a little idea that we are attempting to mine higher material first. I mean, the trend of that is that way. But so it actually is available, it works. This was an opportunity for me to try it out on a real project. The concept of figuring out a footprint, laying out a sequence, and mining it is pretty standard stuff. So that's the end. Well, the story will be continued next year. So I have an end done. Any questions?